The quantum Cheshire cat is a famous experiment that's attracted a lot of attention in the past decade. In this experiment, a particle is supposedly separated from one of its properties, for example, its spin or polarization. It's called the Cheshire cat because that particle is kind of like the cat and its disembodied property is kind of like the grin of the cat. But maybe I should better say there was this famous experiment because it was just debunked in a new paper. Let's have a look. The idea of the Cheshire cat experiment goes back to a paper from 2012. The original idea was theoretical, but it has since been realized in several experiments that have shown that it actually works. So no one doubts that the experiment works as they said it does. The question is what it means. The idea is this. You take a photon and send it through a beam splitter. The photon has a 50% chance to either go straight through the beam splitter or to be reflected. This means that if you describe the photon with this mysterious thing that we call a wave function, then after the beam splitter, the photon's wave function is in a superposition of both paths. So it seems that the photon goes two ways at the same time. Then you recombine the beams using two mirrors and a second beam splitter. And you put two detectors at the two possible output directions. I'll call them detector 1 and 2. This entire setup is known as a Mach-Sender interferometer. It has the interesting property that if the arms are the same length, then the photon goes out only in the direction that it came in. It's because on the other possible output direction, there's destructive interference. So set up properly, all photons go out to the right into detector 1 and never into detector 2. For the Cheshire cat experiment, we then also need a second property for the photon. Usually that's polarization. Polarization, roughly speaking, tells you which way the photon waves twist along the axis of propagation. Doesn't really matter if you don't know exactly what that means because we won't need it. Only thing we need to know is that there are two different polarizations. Let's just call them plus and minus. We start with a photon of polarization plus. If we just send it through the beam splitter, it'll come out the same way, nothing interesting going on. Then we put a polarization flipper on the lower path, which makes the polarization there change from plus to minus. What happens now is that the parts of the photon wave function from the two paths can no longer recombine when they exit the interferometer because the polarizations don't fit together. Then you get a mix of both polarizations on each output port. The Cheshire cat experiment now works by throwing away some of those photons that come out of the interferometer. First, you disregard everything that went into detector 2, and before detector 1, you put a polarization filter that sorts out all minus polarization so that only plus polarization passes. What you have left then at detector 1 has the same properties as the original photon, goes into the same direction, has the same polarization. Now the question is, if a photon arrives at detector 1, which path did it go? Well, remember that you looked only at the photons in the final detector which had polarization plus, the same as the initial one. But on the lower path, you flipped the polarization to minus. So this seems to mean the photon must have come on the upper path. Or to put it differently, whatever goes along the lower path doesn't make a contribution to what goes to detector 1. Okay, so the photon is on the upper path. Now you want to know what the polarization does. Unfortunately, you can't go and actually measure it because quantum mechanics has this funny property that if you make a measurement, you change the properties of the wave function. But you can do a sneaky tiny measurement known as a weak measurement. That the measurement is weak doesn't mean it's stuffed going to the gym. It means that you don't measure enough to get a definite result. Because this definite result is what would collapse the wave function. With a weak measurement, you just change the quantity you want to measure a little bit and see what the result is. In the Cheshire Cat experiment, you just change polarization on this lower path a little bit. You then repeat this for many photons and see what else changes along with this tiny change. It's not irrelevant to note that it's actually a very specific change that they do to the polarization, and it's designed so that if you did this particular change on the upper path, it'll not do anything to the plus state on that path. But if you do it on the lower path with the minus polarization, this will mix some of the plus polarization back in. And this will change how well the interference works at the end of the interferometer, and that makes a measurable change in detector 1. So you've changed the polarization on the lower path, and that made a difference for the measurement outcome. You conclude that even though the photon was on the upper path, its polarization was on the lower path. Because if there wasn't anything there, how could you have changed it? It seems like the polarization has been separated from the particle. This is where the story of the Cheshire Cat comes from, because it's like the grin, that's the polarization, has an existence independent of the cat, that is the particle. The authors of the new paper now point out that these two arguments about the location of the photon and its polarization are both correct, but they can't be correct at the same time. Basically, you can't have your cat and eat it too. Cake. You see, the issue is that if you make this weak measurement to show that the polarization was supposedly on the lower path, then you do this by mixing back in some of the plus polarization. But then you can no longer conclude that the photon must have been on the upper path. You could also put a detector on the lower path, and if that doesn't click, you'd know that the photon was on the upper path. But then you could no longer do the weak measurement for the polarization. So if you know that the cat is on the upper path, you can't tell where the grin is. And if you know that the grin is on the lower path, you can't tell where the cat is. Mystery solved. It's no fun doing these debunking videos, really. It's kind of uninspiring, isn't it? What are you grinning at? I don't like places where hot stuff bubbles out of the ground, but Icelanders have no such issues. They're now almost ready to start a new experiment that'll drill right into a magma chamber. How do they know that this will not accidentally create a volcano? Let's have a look. Iceland is an island in the northern Atlantic Ocean that sits right atop the mid-Atlantic ridge. That's where the North American and Eurasian tectonic plates rub. Those two plates are moving away from each other at a pace of approximately 2 centimeters per year. As the plates move apart, hot molten rock called magma can rise to the top. This is why Iceland sees frequent volcano eruptions and on occasion gets a new island, like this one, which was born in 1963. Not so surprisingly, Iceland has the largest per capita production of geothermal energy, which covers an amazing 66% of the country's primary energy needs. They also really like drilling deep holes to see what they'll find. And boy, have they found stuff. Their most ambitious plan was the Iceland Deep Drilling Project. In their first attempt in 2009, they tried to drill to a depth of 4.5 kilometers near Reykjavik, well above where they thought a magma reservoir was. However, just beyond 2 kilometers, they drilled into an unexpected upper part of the magma chamber. The magma plugged the lowest 20 meters of the hole and damaged the drill. Aggressive gases began bubbling up that also damaged the surface equipment. Eventually, the main valve failed and the well was shut down. They drilled a second hole in 2014 and encountered the same problem. The drill tapped onto a magma chamber where they didn't expect it, and acidic gases wrecked the equipment. You may wonder why they go to these troubles. The reason is, as so often, physics. You see, usually geothermal power plants work by piping water through hot layers underground. This heats up the water, which creates pressure, which can then be used to drive a turbine and create electricity. But water, or any substance really, has a limited capacity for how much energy it can transport, called the enthalpy. And the enthalpy of water makes a sudden jump at about 374 degrees Celsius. I understand that very well, because at that temperature I would also jump. If it gets even hotter, the water is neither a liquid nor a gas, but both. The phase is called supercritical. This may sound a bit obscure, but you can witness supercriticality yourself in my YouTube comments. The amazing thing is now that supercritical water can carry several times more energy per mass, and the conversion to electric energy becomes more efficient. This means if you can build a geothermal plant with a reservoir hot enough so that the water becomes supercritical, that'll suddenly dramatically increase the power production, by some estimates up to a factor 10. Supercritical reservoirs are kind of the holy grail of geothermal energy. There have been a few attempts at supercritical wells in the past, notably in Italy and the United States, but they all ran into some sort of trouble. Either they blew up or they collapsed, or both. And this is what the Icelanders were trying to do with their deep drilling, creating a supercritical well. You might think that hitting upon magma and wrecking their equipment would have discouraged them, but not so. Yes, they had these nasty gases and their drill got stuck in the magma, but it's not like they accidentally created a volcano. Basically, they concluded it wasn't as bad as they thought it'd be. So they're doing it again, but this time on purpose. It's called the Kravla Magma Testbed. They want to drill 2 new holes, each about 2 kilometers deep, first nearby and then into the magma chamber that they know to be there. The drilling for the first borehole is supposed to start by 2026. It'll not drill right into the magma, but just close to the chamber to measure temperature and pressure. They also want to bring up samples from down there. The second new borehole will then actually drill into the magma chamber to test the possibility for a supercritical geothermal power plant. Isn't this kind of dangerous? Yes, it is. But they know from the earlier drilling that while the magma chamber is the pressure isn't high enough to accidentally create a volcano. At least not unless the conditions down there have dramatically changed in the past 10 years. Honestly, I wouldn't go anywhere near that thing. The project has both scientific and technological purposes. They want to study the magma and what it's doing under the earth when it's not bubbling to the surface. And according to the project's website, the purpose of this endeavor is an exploration into the utilization of superhot magma, geothermal energy and fluids that'll revolutionize our energy landscape. Yes, and a bit of magma might even revolutionize your landscape. According to the website New Civil Engineer, the project management's now seeking funding of £79 million for the first stage. So if you have a few million to spare, maybe they'll send you a fresh magma sample in return. Geothermal energy is a rather obvious source of energy. The energy that's contained in the deeper layers of Earth is staggering. Geoscientists have estimated that the total energy reserves in the upper 10 kilometers of Earth's crust would be enough to power the entire world population for several 100 million years. That sounds amazing, but the problem is that in most places finding hotspots underground is difficult. And drilling into them is not only difficult, but also expensive, really expensive. It's also not irrelevant to note that it isn't so uncommon that the gases which are released from underground during the operation of a geothermal power plant contain carbon dioxide. On average, carbon dioxide emissions are low for the currently existing geothermal power plants, though there are some examples in Turkey where geothermal power plants actually emit more carbon dioxide than a typical gas power plant. However, how much they would emit with deeper drilling or new extraction techniques, nobody knows. What all of this means is that geothermal energy is a good solution in some places, and we can almost certainly get more out of it than we presently do. But in most places it's difficult and expensive, and that makes it extremely unlikely that it'll ever become our global main energy supply. And I, for one, am grateful for it, because I don't like hot stuff bubbling out of the ground. I got a lot of questions this week about an article which said that physicists have designed a way to detect quantum behavior in large objects like us. Quantum behavior like what? Going through 2 doors at the same time? Tunneling through a wall? Separating my grin from my face? I had a look at the paper. First of all, this is a really neat paper. It's about what I consider, without exaggeration, the most important question in physics today. That is, why do we not observe quantum effects in everyday life? Like, why aren't cats ever dead and alive for real? I often hear people say that quantum mechanics is a theory only for small things and just doesn't apply to large things like us. But that isn't true. It's really a theory for all things. We know from experience that large things like you and I don't seem to be able to do quantum things. At least I haven't tunneled through any walls recently. But the thing is that the mathematics of quantum mechanics doesn't have any such distinction. This is why Schrödinger was going on about this cat which is both dead and alive. His point was to say that this is one of the consequences of the mathematics of quantum mechanics. Yet somehow macroscopic objects don't seem to display this quantum behavior. Now, since Schrödinger's days, physicists have solved part of this riddle. They have figured out why it's basically impossible to measure the quantum properties of large things like cats. It's because of a process called decoherence that has the effect of spreading quantum links into the environment until you can no longer tell they exist. But all this decoherence does is that it converts a cat which is in this funny dead and alive state into a cat that's dead with 50% probability and alive with 50% probability. This is no longer a quantum state because now you have normal probabilities, but it's not what we observe either. So physicists solved the question why we don't observe quantum properties of large objects, but they haven't figured out why objects always exist with probability either 0 or 1. One way to explain this is that quantum behavior indeed goes away for macroscopic objects. If that was so, this would be a really, really big deal. Because as I said, quantum mechanics itself says that quantum behavior does not go away for big things. The trouble is, it's very difficult to measure this. The authors of the new paper now put forward a very clever idea. They propose to track the path of an object to see whether it makes quantum jumps. You see, the key feature of quantum mechanics is that it's fundamentally random. So quantum objects sometimes change direction or location for no particular reason. The question is then whether large objects still have this kind of unpredictable change in their behavior. The trouble is that, well, if you track the path of an object, it seems you need to measure it, and that'll disturb the object, and that'd look like a change, but it wasn't a quantum jump, it was something that you caused. The cool thing about the paper is that they figured out a way to measure the path of an object without ever looking at it. This may sound somewhat counterintuitive, just maybe, but the idea is really fairly simple. Suppose you have a big box with a marble inside. There's no light in the box, so you don't know where the marble is. You want to know where the marble is and whether it's doing quantum jumps. But you don't want to shine any light on the marble because that could oh so slightly move it. What you do instead is that you only look at one side of the box. And if you do not find the marble there, you know it's on the other side, even though you never looked at the marble. This is called an interaction-free measurement. The researchers now devise a protocol in which you do this repeatedly by updating which part of the box you measure to gather information about where the marble is. And importantly, they show that this kind of measurement does not depend on the mass of the object. So it should work for heavy objects, in principle as heavy as you and I. And this is where the headline came from. It's that their protocol for inferring quantum properties of an object doesn't depend on the mass of the object. But as usual, the devil is in the details, because while their protocol is in principle independent of the mass, in practice making the measurement becomes more difficult with mass. This is because, as you may have noticed, heavier objects also tend to be larger, and the larger they are, the more particles they are made of, and the more particles they're made of, the noisier they are. There's also the issue that I suspect it won't be possible to tell apart a truly random from a possibly chaotic motion. Still, I find this a very intriguing idea, and I can't wait for the experiment to show that if I just hit my head at a wall often enough, I'll indeed eventually tunnel through. The Center for Countering Digital Hate put out a new report a few days ago in which they warn that climate misinformation continues to flourish on YouTube. They want YouTube to take more action. Let's have a look. The Center for Countering Digital Hate is an American-British non-governmental non-profit organization. For their new report, they use artificial intelligence to crawl YouTube videos and to classify all types of climate misinformation that they came across. They found that outright climate change denial, that is, claims that the climate isn't changing or that humans are not responsible for it, have strongly declined. Instead, the majority of climate misinformation is now what they call the new denial. This encompasses claims that acknowledge the climate is changing and we are causing it, but it's nothing to worry about, or it's actually good for us, or if it's not good, then we can't do anything about it anyway. To the new denial, they also add a general dismissal of climate science or climate scientists as unreliable. Their analysis found that this new denial now makes up 70% of all climate denial claims made on YouTube, up from 35% 6 years ago. This shift has been going on for some years, and you'll probably see the new deniers in the comment section below because they like to follow me around. It's the type that claims carbon dioxide is good for plants, therefore all is well, and all climate scientists are frauds, and so on. The main reason for this shift is probably that it's simply become futile to ignore the evidence for climate change. A secondary reason may be that YouTube doesn't allow monetization of videos of the old denial type, whereas the new denial type can still be monetized. Personally, I think that's only a small part of the reason, because we've seen the same shift on Twitter, which until recently couldn't be monetized at all. The report contains quite a few examples of videos that use the new denial. Most of them have few views, but some of them go into the millions, featuring people such as Jordan Peterson or being produced by Prager University. The center estimates that YouTube makes more than $13 million in revenue each year from the new climate denial, which doesn't sound like much unless it's in your own bank account. The Center for Countering Digital Hate then calls on YouTube to update its policy. The current policy is we do not allow content that contradicts authoritative scientific consensus on climate change. And the policy they recommend is we do not allow content that contradicts the authoritative scientific consensus on the causes, impacts and solutions to climate change. They also recommend more demonetization on YouTube and other social media. I see a big problem with that recommended change in policy. It's that it's crossing over from limiting the spread of scientific misinformation, which I think is a good idea, to attempting to streamline people's opinions about how bad the situation is and what a good solution will be. It's crossing over from facts to opinions. If someone claims that plants will benefit from the sudden change of climate zones, then that's scientific misinformation, all right. If someone says that they're not worried about climate change and more worried about energy shortages, then that's their opinion. And depending on where they live, that opinion might not be all that crazy. Indeed, you could also argue that I myself count as a new denier according to this center, because I've made a video explaining why I think all current plans to reach net zero are almost certain to fail. So let me say this bluntly. I'm not in favor of a policy change of this type. I'm not happy, of course, that some people are making money peddling nonsense, but the problem isn't the few people who produce this content, it's the many who watch it. The problem is that a big part of them wants misinformation. They want misinformation, consciously or subconsciously, to justify conclusions that they hold dear, whether or not their reasoning is sound. This is why I doubt that bans or demonetization are going to make much of a difference for the spread of misinformation. If there's demand, there will be supply. Market forces alone won't fix this issue because ads target the viewer, not the video creator. This means brands don't really need to worry that they'll be associated with content that the viewer dislikes, because the vast majority of people click on a certain type of content because they like stuff like this. Personally, I think that the best way to combat misinformation is with information. I know that that's very old school and that some studies seem to have found that people rarely change their mind when given new information, but I'm somewhat skeptical about the reliability of psychological studies. Also, the very fact that the old climate denial is on the decline speaks against it. People do evidently change their mind when confronted with facts. But yes, scientific misinformation is a really difficult problem, and it's bound to get much worse as more AI tools become available. I hope that someone somewhere knows a good solution, because I don't have one. Though maybe you do. Let me know in the comments.